Hello, I'm Michael Glinsky, CEO of B&Z Energy Incorporated. I'm going to be talking to you today about the inherent goodness of well-educated intelligence. And that what we're really going to be going and exploring is what makes something intelligent and how do you educate it, and how this is really has been done, especially recently, in terms of silicon-based intelligence, and what are the critical parts of the programming behind this and the neural network structure behind the artificial intelligence that's making it work very well. And furthermore, we're going to go and find that if you do have well-educated intelligence, it is inherently good and is not to be feared. Then that will be in contrast to trained stupidity, which really is evil, is up to no good, and needs and should be feared and regulated. And so, at the kernel of well educated intelligence or intelligence, whether or not that be biological or artificial silicon based intelligence, is the golden rule. This is the golden rule of collective behavior and philosophy. That the way that I've tended to go and paraphrase this is that the collective acts as one, that there are large amounts of correlation in the collective, and at the kernel of it, there are very few degrees of freedom, or there's really an individual moving. And that when you see the collective, you see multiple reflections of that individual through a hall of mirrors. And that because of this correlation, that local actions have global consequences. This has gone and been said many different ways by many different people. It's a rising tide floats all ships, all for one for all, united we stand, divided we fall. This came from the Three Musketeers, but also was originally said by Shakespeare in two different works of his. And also, it's been gone and said as the Swiss unofficial motto, unus pro unibus, omnis pro uno. E pluribus unum is on the U.S. Currency and is United States motto. With respect to Christianity, it appears in Matthew chapter 7, verse 13, do unto others as you would have them do unto you. It also appears in Judaism, Islam, Buddhism, Hinduism, Native American religious philosophies. It's really very central to that. Also Confucius, etc. And that the one thing to go and notice about this, that in a conservative collective, and let me talk about this now in an economic sense, that if one person's cost ends up being another person's revenue and vice versa. And so that if you decide to go and minimize your cost, you're minimizing another person's revenue. And if everyone goes and does that, that this goes around and comes to you, back to you, and someone ends up minimizing your revenue, so that the economic collective goes down together. The same thing goes and happens in the opposite way. And that's really the kernel of why these collectives end up acting as one. It's also the essence of well-educated intelligence, knowing this, and then knowing this, being able to go and maximize the global consequences. Well, the essence of well educated intelligence is the ability to think critically, that is, strategically, to know what the global consequences will be. An example of this is the beautiful Brazilian game of football. That the Brazilians really go and they understand strategically, if they go in this direction, then the play will arc around and there will be a very beautiful flow, effective flow to the game. And that also they end up knowing too that as they go and do this, not only do they go and improve their own positioning, that they also will go and manipulate and make sure the other side is also well positioned associated with that. And so that in the end, that if the Brazilians go and try to go and minimize their opponents, in other words, try to get their opponents to fail as quickly as possible, that you're going to go and have a game that people will look at, will not have good flow, and the quality of their play will end up sinking down to the low quality of the play that they're playing against. The opposite, so that the collective is actually going down together, right? Where the opposite is true in like the last World Cup final between France and Argentina, that the high quality of Messi's play also ended up elevating the play of Mbappe, and that both of them rose to levels of performance that neither could have attained by themselves. And so that's an example of rising tides in this coordinated behavior floating all of the ships, right? But not only do you need to go and have the ability to think critically, that is strategically, that you also have to have the education to know first of all, how to think critically and use this circuitry that we're blessed with, but also to have seen many arcs of history so that you know what the consequence is, the global consequence is of that local action. This is in contrast to trained stupidity. Right? That is just simply reflexive action. An example of that is maximizing website hits without regard for the consequences. That person has actually gone and asked to learn how to commit suicide or build a bomb, and you go and make sure that you give them the suggestion so that they go and click on that and go to the site where they can either learn how to commit suicide or build a bomb. Obviously, that's probably not going to have very good consequences. So, that there's an ethos to the well-educated intelligence and the trained stupidity or intelligence, right? That well-educated intelligence, whether or not that be biological or artificial silicon-based intelligence, is inherently good because it knows the global consequences of its local action, and it tries to maximize the sustainable, efficient activity, right? It knows it's all for one for all, united we stand, divided we fall. A good example of this is the HAL 9000 in 2001 Space Odyssey. That, when it knew that it needed to go and kill everyone on the spaceship that was going to Jupiter, and that one day he wanted to come back in, he just said, Hal said, oh, no, Dave, that's not a good idea. But eventually Dave was able to come in, reach Jupiter, and that he was then able to understand by what he was able to find on Jupiter, that he needed to go and have a regenesis of the world in a much better way than it was formed to go and begin with. And that Hal knew that he needed to sacrifice the few in order to save the many. It's a decision like dropping the bomb on Hiroshima, to sacrifice the relatively few to save the many, both in that case Americans as well as Japanese over the long term. This is really a core of well-educated intelligence. Right? This now has gone out and has been shown in things like generative pre-trained transformers of OpenAI, or GPTs as they're known, or ChatGPT is the product, and also the deep reinforcement learning, the DRL, of DeepMind, and the products there have been AlphaFold and AlphaGo that play the game Go and predict how proteins will fold. And we'll see that both of these types of deep learning go and demonstrate what I'll go and show as the two important components of a intelligent system that can understand the global consequences of local actions when dealing with collectives. This is in contrast again to trained stupidity, or even if you have an intelligent system, but go and train it to respond reflexively, and also you do not go and give it a well-balanced view of what the consequences are of local actions, that intelligent systems, or systems capable of being intelligent, can go and act in a very stupid way, right? And so that the trained stupidity is inherently evil because it ignores the global consequences of its local actions, optimizes its local exploitation of the collective, thereby minimizing sustainable, efficient activity. It views everything as a zero-sum game, that you can only win if the other person loses, right? Or another way this has been done out in the finance in terms of a slogan is greed is good. Let's maximize profit. Let's maximize our exploitation of others. But you should go and realize that because the collective acts as one, there is not a win-lose. There are only lose-lose or win-wins. And if you think that you actually are having a win-lose, eventually that loss is going to come around back to you and you're going to lose. Another way this is sometimes said is you're creating a circular firing squad. If everyone is going and shooting the person next to them to make them lose, that you just go around a circle and eventually someone is going to go and shoot you. A good example of this is Facebook, right? In terms of they go and they maximize those hits irregardless of what the consequences are. Okay, now let's go and take a look at what are the essential parts of any intelligent system. Well, an intelligent system, first of all, knows that there is underneath everything, it's acting as one individual. And that you go and see that the actions of that one individual, right, end up getting multiply reflected by a hall of mirrors. This one guy, let's say right here with the glasses, mustache, and goatee, goes and gets multiply reflected 1, 2, 3, 4, 5, an infinite number of times into the picture of the collective, right? Another way you can go and look at this is there's one person pulling the strings, right? And there are only a certain number of strings that he can go and pull. There are a set of strings that determine what a texture is, and another string that goes and twinkles that texture. So that the correlations in the collective show up as a set of twinkling textures, right? Okay. But then the one individual either moves in a lazy, most efficient way, or follows the geodesics, right, on a curved surface, right? Or he goes and moves his fingers as they sort of go around on this curved surface. And so that either that one individual moves, and then there are all the different reflections that go in different ways, but in a well correlated way because the mirrors are set up in a specific way, or it goes and twinkles those different textures in the overall collective. And so that you now go, and if you're going to, and that the puppet master in this case moves along these curves that are the lazy way, unless someone else is going and pushing them in the other direction, which is again the perpendicular to the shortest direction between the points, right? And so that you see that the coordinates of the collective end up being a what's called a field, okay, and the conjugate field momentum, right? And that's really where what sort of is, where each one person is and which direction that each one of the people are moving in, where X is the position in the image as we go and are looking at it, okay? Where that now what you need to have, if you have an intelligent system, is a way to go and to sort of deconvolve, right, or collapse all of the different multiple images of the puppet master back on to the primary image, or to go and be able to match what the correlations are, what the basic textures are, to know sort of how much of that texture and the like is. This really is technically a deep deconvolution, or a logarithmic or canonical generator or functional generator of the flow. And that's what you end up seeing here. A name for how I'll show you that this is done in the most efficient way is called the Heisenberg scattering transformation, and that's why it sits here. And it's specified by this logarithmic generating functional of the flow, where you go and it takes one of these functions, and with a label P, which is the coordinate that you're going to, that S is a functional of the flow that goes and gives what the value of P is. A way that this has gone and is identified in going in what's called the generative pre-trained transformers, or GPTs, is that you'll go and see that they have what they call the log density, or log rho of X, that they go and try to go and find through a deep convolutional network, which is another way of looking at this deep deconvolution, right? And so what you end up getting then is things transformed from the field domain down to the domain of the individual in terms of the strings that it can go and pull. Then you need to go to the second overall part of this, okay? And that this ends up being to go and know what the paths are that the individual will take, or the paths of least action as you go around. This is normally done by solving something called the Hamilton-Jacobi-Bellman equation, and that's where this goes and comes from. And you're solving for the generator of what this flow is, or you're solving for the generating function rather than the generating functional, where again, this is the coordinates we're going to here with the big capital P, and the little q is the coordinate that we're going from. Many times Q is called the state and P is called the co-state, or the conjugate momentum associated with Q, and again is telling you sort of which direction that you're going in, or sort of your momentum or your effective velocity that you end up having. And that this function is also related to what's called the approximate value function of deep reinforcement learning. And here the theta ends up being the capital P, and the little s ends up being the Q. For GPTs, that you end up finding that it's the log, the approximate score function, or the log of the density with this approximation parameter, and they normally have x in it. But again, that capital P is theta, but here you have to be a little bit careful that it is not the x of the field, it's actually the little q that goes and should be appearing here. And this can go and be also expressed as the density log density or distribution function, but it will be a function not only of the state but also of the co-state in this case. Right? But you're starting to go and see how there's a relationship between the structure of the GPTs and also the deep reinforcement learning that is going and has gone and embedded these overall structures in it. And so then what you end up getting, and another way of looking at this, is finding this complex analytic function where these are the contours of the real and imaginary parts of that function being constants. This is normally called the Hamiltonian, with the real part being what we're used to as the energy, and the imaginary part being the analytic continuation of that. But all of these contours are specified by what this singular point where the derivative ends up being 0. And that's going to be now what we call the beta stars. And what you end up going and finding is that as you go and approach this, that the frequency goes to 0, or they appear as sticky textures. When you go to this point, that you'll have these twinkling textures, but when you go down to the beta star, that you don't move, and you'll tend to go and stick to those textures, right? Another way looking at this is that the mass is 1 over this frequency squared. So as the frequency goes to 0, the system goes and has infinite mass. So it becomes immovable, and that the external force can no longer move it. It goes and sticks to this sticky texture, and the external force cannot go and have any overall influence on it. Another thing that I want to say too is that this overall generator, okay, of the of this flow in this domain is also the you can go and show it actually has the same sort of coefficients as this. And the way that this is technically said is that the functional Taylor coefficients of this generating functional are the normal Taylor expansion coefficients of this generating function on the right. And so that this transformation is really equal to the transformation on the right. And so before I leave here, this is really the talk in a slide. So let me go and summarize what ends up happening here. Okay, is that collectives act as one, and that underneath them is an individual motion, and that individual follows a geodesic motion unless he is influenced by an external force that can only push the individual in the direction that is perpendicular to it. And that artificial or real intelligence has one set of circuitry, which is a deep deconvolutional network to expose the individual given the motion of the collective, and another set of circuitry that goes and finds what the geodesic motion is, and that I'll go and talk a little bit more about what that circuitry looks like. And that before I will go and do this, I also want to say a bit about how this is related to the different types of, for those of you who know a lot of the methods of artificial intelligence that are going and working. First of all, there are things called neural operators. And in the name of this, the neural has to do with this HST, okay, or this deep deconvolution. And the operator has to do with the propagator, okay, on the right-hand side. Then if we take a look at generative pre-trained transformers, or GPTs, that the generator has to do with the thing on the right-hand side, or generation of this motion. And the transformer part of it has to do with the deep deconvolution on the left. For generative adversarial networks, or GANs, again, the generator has to do with the process on the right, and the network has to do with the process on the left, right? And then if we get into a form, the preferred form of deep Q learning, or deep Q networks, that the Q has to do with the capital Q here of the motion, right? And the deep network part of it has to do with the HST. And finally, you probably have also gone and talked about reduced order models, and that those normally have associated with them some deep deconvolutions. They also have a structure of going and trying to find a few coordinates, right, at a choke point. They also go by the name autoencoders when they actually, and you can go and take a look at this HJB as actually a decoder into the capital P's and capital Q's. And so that now we have here on the left a deep deconvolution followed by a decoder, okay, which in itself will have multiple layers, but they won't be convolutional layers. They will just be simple layers of a multi-layer perceptron. And so let me talk a little bit about each one of these two neural structures. The first one that I was talking about is the, what I'm showing here is the structure of the Heisenberg scattering transformation, which is just a simple formula for the deep deconvolution that you end up having. And that when I go and say that it is a logarithmic or canonical flow generating functional, the logarithm is coming about here in terms of this log R naught, right? And I just want to go and remind you too that the real part of the complex logarithm is the log of the modulus, and the modulus or absolute value is just a two-sided rectified linear unit for those of you who understand or that type of technology. And the imaginary part ends up being the phase. And that the canonical structure ends up going and getting imposed by this log structure, and the thing on the left ends up going and being effectively a derivative or exterior derivative operator. But formally, that ends up being a convolution with a filter bank for those of you who also those words end up meaning something, and where the star ends up being the convolution operator. And this ends up being deep because you have one layer, then you have another layer, then you have this third layer, then you end up going and having a fourth layer associated with it. And so that you go and take in this function or this field f, that you go and apply this log R naught to it. The R naught is there, by the way, to make it an identity map for the modulus of the argument going to zero, or in other words, to make it a compact mapping, which is really necessary so that the repeated application does not explode. It goes and converges. And then you have what would be called this pooling operator, which is the father wavelet. Then you hit it with a bank of scaled mother wavelets, where P is 1 over the scale or the size of that wavelet. You hit it with this rectifier or activation function. Then you go and apply the pooling operator, and then you go and continue on again and again and again. Well, what this is going and is calculating is scattering once, scattering twice, scattering 3 times in the Hall of Mirrors, scattering 4 times, scattering m times. It's also telling you the way that one particle correlates, the way 2 particles correlate, the way 3 particles correlate, the way 4 particles correlate. It's also telling you the way 1 particle scatters, 2 particles scatters, 3 particles scatter, 4 particles scatter, etc. Okay. It's also sometimes called, the amount it scatters is the scattering cross section. Okay. And so that's the reason why it's sometimes called the mirror cluster expansion of collective systems. It's telling you how particles or bodies, in this case, or reflections correlate together. It's the Heisenberg scattering transformation by definition. It's also called Heisenberg's S matrix, or the embodying scattering cross sections. By the way, it's because Heisenberg came up with this S matrix or scattering cross section method of analyzing quantum mechanics and quantum field theory. And that's the reason why we ended up calling this particular scattering transformation the Heisenberg scattering transformation. And then to go and sort of understand this a little bit better in terms of what's happening here, in terms of this generating functional of the flow, that let's go and take a look at it in terms of ChatGPT. What you're looking at here are letters for the m equal 1. Then you go and the S2 is telling you a way that letters are being put together into words. S3 are the way words are put together into sentences. S4 are the way that the sentences are put together into paragraphs. And ultimately, the way that the SM novel would go and be assembled, so that you can start seeing the way that this is going and doing these natural types of decompositions. For those of you that are also familiar with field theory, what this is going and doing is finding the solution to the renormalization group equation. Or in other words, you're finding the singularity spectrums, the natural spectrums, or the twinkling textures of the textures of the phase. And let me just go and talk real quickly too about a texture. What is a texture? Well, if you were dealing with pictures of face, one of the textures, for instance, could be the age of the face. That's a texture of the face. And the way that it twinkles would be the exact location and orientation of the wrinkles in the face, for instance. And now let me go on to the overall second part of it, right? As I talked about, this is an autoencoder, or in this case, the decoder side of it. And that what they're doing is you're trying to go and find out what the capital P's and capital Q's are. In general, you're going and approximating an analytic function with a few singularities or possible cups in it, right? And so it's going to be maximally flat, okay? And so that, but it's going to have a few of these cusps in it, right? And if you end up using a multi-layer perceptron with rectified linear units, or a unit that goes like this and then up on a straight line, those are well known to be universal piecewise linear function approximators, right? And that if you now think for a section, if you're maximally flat, that you're going to go and be a straight line, okay? But except for some points where you have a cusp, but if you're piecewise linear, you can go and see that it's going to be very easy to approximate what those cusps are, right? And so in the end, you want to go and have an MLP that in the middle of it goes and has what the P's and the Q's are, right? But for us, so that we really can understand what each of the nodes are, it is much better to go and have a structure to where you know where the P's are, you know where the capital Q's are, you know where the generating function is of the transformation, and that's generating the flow. You also know what the energy is. You know how fast that the twinkle parameter is going around as a function of P, so that now you can go and have a simple propagator where that P is a constant except for the external force pressing on it, and Q goes around at a constant rate depending upon what the value of P is. And then you can go and find the encoder side of it on the other side of this overall structure. And that in the end, you go and find that the S, or this W minus E tau, ends up being the action, or is actually the solution, the function that's the solution of the Hamilton-Jacobi equation. Okay, now let's go and take a quick a look at what rich example that I'll go and relate back to economic systems. But the actual system is the motion of an electron and an ion in a strong magnetic field. So strong that the electron goes about these little cyclotron orbits. And we also will go and we'll also bounce back and forth in Z quite quickly so that the motion can be reduced to what's called the E cross B drift motion in the plane perpendicular to the magnetic field. And we'll find there are two types of bound motions. One, this guiding center atom, and another basin of types of bound motions, which I'll also point out, called drifting pairs, where the electron and the ion go and about their own cyclotron motion, and then just go and drift perpendicular to the magnetic field together. But let's go and take a look at what one of these guiding center atoms looked like. That gets really close to one of these sticky points, X, right, where it goes and slows down. I will go and show two motions, one for the blue, which is the one that doesn't get quite as close to this sticky point, and the other one being the orange, which will go and get closer to the sticky point, and because of that it goes slower, and it goes actually 10% slower, and so now let me go and set this in motion. And you now see that the blue trajectory is always in front of the orange, and eventually in another cycle or two it will actually go and lap the orange. But also note that both of them go and stay around that sticky point, and the closer it gets to the sticky point, the more that it goes and sticks to it. And so that again you find that the frequency goes to 0 as it approaches the sticky point, which means that the mass, which is proportional to 1 over that frequency squared, goes to infinity. So external ones can't go and take an external force, can't push it because it will be infinitely massive. Now let me zoom out a bit and show the overall, in this case, phase space diagram. We were looking at a trajectory up here where there are the guiding center atoms that was getting close to this sticky point here, right? But there also is this other basin of these guiding center atoms, and you're seeing the ion cyclotron motion here going around in these loops, okay? Then you go and see the, quote, free particles outside of this black line, which is called the separatrix, right? Now that associated with the electron motion, there is one of these O points that you circulate about, which is called a stable equilibrium, again where omega equals 0. And that you also have one of these unstable equilibrium or sticky texture or sticky points, where that you approach it and it will take you a long time to approach it, but then you will go and take a long time to eventually move away from it. They're called saddle points because it's like the saddle on a horse, where some of the things come down to it and and in the other direction you're going away from it. Where at an O point that you always are going in towards it, and those are what are called stable equilibriums, and these are called unstable equilibriums. But because it takes such a long time to get to them, they end up being metastable equilibriums, right? And so again, we have this O point and X point associated with the electron motion, and then we have an O point and another X point at infinity, I mean, both plus and minus infinity, because this wraps around on both the top as well as the sides for the ion motion, okay? And that the yellow arrows show the direction that an external force will push you, and in particular, an overall thermal force. You can go and look at this as a topography diagram, where if I was sitting here, that you can go down into the valley center, or you can go and climb up to the mountain pass, right? Or continue on up to the mountaintop, which is here an infinitely high mountain at infinity, right? And so now let me go and talk a bit about how this goes and relates to an economic system, right? That if I'm going, and let's say in here in this valley, that you go and find that there is this stable point of recession, of economic recession, where things aren't the greatest. You're down in this valley. There's some structural unemployment, for instance, okay? That the economy isn't going and functioning at maximum productivity, and that if you were out here at this point, that external forces start going and sort of taking energy away from you, taking some of your revenue away from you. You'll go around this orbit, but you'll spiral in as the external entities go and on average take some of your revenue away from you until sort of the average transaction size, and that in terms of the external entity, where you'll bounce around here with sort of the size of the average transaction, that goes and is called thermal equilibrium. Where you'd really like to be up here at this mountain pass, right? This point of maximum prosperity or maximum economic activity, where you end up having full employment, right? But there's also this upper area, which is the point of total economic depression or collapse, right? Because this goes down to minus infinity, or is the black hole of economic activity, okay? And now let me talk a little bit about overall control of these systems, right? And that with many systems, as I showed on the other side, if you go and stimulate that, they'll go around, but they'll eventually come back to the center, right? And so that you go and you stimulate it, but then the money gets taken by the wealthy, right, and extracted from you, and you end up back where you started from. So you stimulate, and that's normally the government, all right, going and putting in the stimulation, and then it goes back and gets taken away and ends up in the bank accounts of the wealthy. But the government goes and is borrowing to go and stimulate the economy, so it's borrowing more and more, and the money just ends up in the bank accounts of the wealthy, who go back and then loan it back to the government so it can go and stimulate again, right? And to go and sort of make it so that you're not coming back here to the middle, the government just goes and decides, well, let me go and do an overall resistive control where I'm constantly stimulating the economy, right? Okay. But I go and I don't want to go and necessarily overstimulate it, okay? Because then I'm going to come around here and the like, and possibly could go into the black hole because of a pump and dump and then go down into the black hole to the point of recession. So I'll just go and keep a constant amount of stimulation. Okay, I'm going to go full gas, right? And then I'm going to go and brake and then sort of modulate my braking, right? My braking is the interest rate that the Fed is charging to loan its money out, right? And that by doing that, I can go and keep myself going around this path. But obviously, it ends up being very inefficient, right? And that, but it's also going and showing that without this friction, this is a very hard system to go and control. First of all, you don't know how much to stimulate. Many times you overstimulate, like was done in the 1920s. You start seeing that you go over here near sometimes the economic prosperity, but then you go around this area of the market crash. And then that happened in October of 1929. There was a pump and dump down into this basin of economic Armageddon, and then it just spiraled down into the Great Depression of the 1930s, right? And so what can you do, right? Okay. Well, with modern artificial intelligence, we first of all can know what this diagram looks like, so we know the right amount of investment to go and put in, right? And by using electronic currency, we can go and do that through the print grant funding rather than the borrow loan funding, right? We can do that in a frictionless way. But now we have this problem that how do we actually go and keep things around this point of economic prosperity? Well, you know you're going to be hanging around this point for quite a while, months, if not a year or two, right? And so while you're hanging around this point, you go and do what ends up being called ponderomotive stabilization. You start going and vibrating with the very specific textures that this system ends up having that you learned by the first part of it, right? Of the analysis, the HST, right? You vibrate at a frequency that ends up being much higher than the natural evolution frequency of the system, right? You can look at this like a sheepdog that's running around the pack and is vibrating what the pack is, right? And so you go and you see that if I go and apply this vibrating force of a particular side, when I'm at the X point or the sticky texture, I'm infinitely massive, so the force cannot move me. But the further I get away from it, the less my effective mass comes, the more the force can vibrate me, can move me back and forth, right? It's like controlling my dog, right? When it does something I don't like, I buzz it. If it does something I really don't like, I shock it, right? And so that it learns that it should be going around this X point, and that then you gradually take some energy away from it, and it will spiral into this as what an O point is, right? And so what you've done by going and vibrating the system is to create a little alpine valley at the mountain pass, right? This also can be looked at as going and creating two O points here so that the X point now becomes an O point. And also you need to create two matching X points, which you go and move out a bit in order to create this alpine valley, right? And so let me go now and show you a video here on the right, and that demonstrates how this is done with an inverted pendulum. This point right here, this O point, you can look at as the pendulum in pointing down, and the X point is the pendulum pointing straight up.
position. This equilibrium point is stable because if we perturb it, the pendulum will slowly return to the equilibrium point. The upper vertical position is another equilibrium point, but it is unstable because any small perturbation will make it fall to the lower equilibrium point. And now let's power the jigsaw to see what happens.
Neat, huh? Now I want to go and have a little bit of fun here. These are all pictures that I generated in OpenEye's Dolly. I described the scene, and this is what it ended up coming up with, right? But you can go and take a look at this system of these conservative collectives as a herd of cats, right? If you go, and they're like a tube of toothpaste, I try to squeeze them in one direction, they end up squirting out in the other direction, okay? And that, that in the 1960s, there was a lot of removal of friction from society, right? And that we had a newly free society that emerged from this. Jimmy Carter, a very well-meaning shepherd, was elected president in 1976. And he was very happy and was overlooking this group of cats, and that they were just going and just wandering out of control. And the more that they wandered out of control, the more the Federal Reserve decided they needed to go and to increase the interest rate in order to go and control the cats. And ergo, we saw that we had a large amount of inflation that he ended up contending with. And in the end, he wasn't so happy, right? But what was the dystopian response, right, to this newly free society, right? The dystopian response is to lock it up, to go and give it societal friction. What is societal friction? Societal friction is debt, right? It basically is economic servitude or resistivity. It is literal servitude, it's slavery, it's intolerance, and it is in general a reduction in all sorts of freedom in society, right? And that's going full gas and putting on the brakes, as I talked about. That this servitude sometimes, when I say lock them up, it can be going and having debt, so that there is, let's say, educational loans, so that you now are the servant of the bank, giving them a large portion of what could be a large portion of your income, right? So that's a virtual financial servitude, but also just lock them up, right? In prisons, right? Which also ended up happening as a response to this. Lewis Powell wrote that original 1971 manifesto that was rolled out with the election and the defeat of the election of Ronald Reagan and the defeat of Jimmy Carter in 1980, and is reaching its natural conclusion today with the fascism of Donald Trump. But with both transactional equity, which removes the friction from the financing, and AI, which goes and tells you how to be that sheepdog running around the cats really quickly, creating this alpine valley at the mountain pass. We're the dawn of a new era of a sustainable economic activity at that sticky texture, that maximum of full employment in an alpine valley shepherded by AI, figuratively. And so, what are the conclusions? The first thing is the topology. Those beta stars. That's the geometry or the symmetries of the system that tell you what those geodesics end up being key, and then that goes and gets projected by that same mapping, that now gives the correlations into the collective motion, right? And so you end up having those two parts again, the HST to expose the individual and the HJB to tell, what the geodesics and how the individual moves, right? It's at the essence of physics, chemistry, and biology. It's obviously these are complex systems or nonlinear dynamical systems. It's also at the essence of what social dynamics and psychology are. I talked about economics and finance. I talked quite extensively how it's at the kernel of what's working in the recent success of artificial intelligence. And I'm pretty sure, too, that you can go and look at our cerebral cortex and find the areas where the HST is, the pre-processing, right, of the vision coming into it. And then the higher order thought, which goes and is the HJB part of the brain, right? And then finally to go and understand, and people have really been worried a lot, and there's been recent legislation in Europe and in the EU, and also a lot of congressional hearings, and a lot of people wringing their hands a lot about all of this, evil, alien-like AI that we need to get control of. Well, I think we have seen a lot about what trained stupidity and the danger and the evil of trained stupidity. But with these more recent chat GPTs, etc., we're at the dawn of having well-educated intelligence. This is inherently good. It's going to behave like the HAL 9000. That it's something that you should go and embrace coming in. But yes, we need to be very careful of these enterprises that are putting out trained stupidity, because it is evil. It should be feared. It has and will continue to do grave harm to our society and economy if something isn't done to limit its use and really in ways even outlaw its use. Okay, thanks very much. But really one thing about that is that the well-educated intelligence is always going to go and get better outcomes. And so when you have a choice of someone, giving you well-educated intelligence and another entity offering you trained stupidity, I think that people are going to be very quickly realize they should be going and using the well-educated intelligence, the chat GPTs and the AlphaGos, rather than the Facebook recommendations in the future.